Hello, friends. Welcome to Dynamics Hour with Dr. Hart. I will be your instructor, Dr. Hart. Your exam is tomorrow. Hopefully you've been studying, or at least trying to study, or so on and so forth. That's really the only announcement today. You don't have any homework to do, you don't have any simulations. All you really got to focus on is taking care of business for this exam. All right, so I posted practice problems for you guys. I posted the solutions along with those, though I will admit that there is a mistake in the solution for problem number 6, which I just noticed before this class. So I'll be updating the solution for problem number 6 on the practice problems in a little bit, but that's for a later date. The exam tomorrow is going to be basically just the exact same as it was for the first exam, how the logistics are going to work. Come to lecture a couple minutes early, get all your pencils and papers in front of you and ready, have your equation sheets, so on and so forth. It'll be open everything, MATLAB, internet, notes, what a calculator, whatever you want, okay? Open everything. Just make sure it's you doing it, okay? You can use a calculator, you can use MATLAB, but you can't use your brother, all right? Turn your camera on, point it in the direction of your work, keep your microphone muted, all the stuff that we basically had before. All right, you'll get 50 minutes to do the test and 10 minutes to turn it in. So I'll need to have your work by the 4 o'clock deadline. And I'll distribute the exam in the same way. I'll post it to Blackboard, and I'll also email it to you individually when the exam starts. So that's how it's gonna go. There will be 2 questions on the test, one on kinetics, one on work and energy. Any questions about the test? Anything in the chat? Nothing in the chat. Okay. I will quickly construct for you what I think is going to be a good equation sheet for this test, though most of the stuff I hope that you kind of have in your head and memorized already anyways. All right, so I'll get you over to the white pad here, and then I'll put down what I think is kind of like a good equation sheet. What do you think of my meme today? Patrick, 3, take it or leave it. It's a little unclear to me whether he means like 3 significant figures, like it should be 3.14 and E is 2.72. Okay, that's fine. 3 significant figures, that's appropriate. Or if he just means like the value of 3 for both those constants. Yikes. If that's what he means, I'm nervous. I don't want him building my house or my pineapple if you're SpongeBob. All right. Let's do this thing. 3, take it or leave it. If you write that on your test, I'm leaving it. All right. So what I think a good equation sheet might look like. All right, you're going to want information about kinematics. And this should be sort of stuff that you had on your quote-unquote equation sheet for exam number 1. And that is something like the acceleration of point A is the acceleration of point B plus the angular acceleration crossed with the position vector that locates A from B plus omega cross position vector which locates A from B. Hopefully you've got that one burned into your memory. You've done that enough now where I hope that it's in there. Forever and ever. Velocity of A, velocity of B, plus angular velocity crossed with position vector that locates A from B. So those are your kinematic relationships. We've used those a couple of times throughout the duration of this portion of the course, so those things don't go away. I told you that before. We're going to write these 100 times in this class, and you're going to like it. You may also use the kinematic relationship that's something like the magnitude of V is R times the magnitude of omega. So that comes up a lot. V equals R omega. You saw that kind of a lot on your work and energy homeworks, and that comes up from time to time. But you have to know when that equation is useful and when you want to use that equation. And all this here is derived from that. So even if you don't like memorize that or know when exactly to use that, you can always go back to this guy to get you through it. So that'll be like kinematics that you might want to have at the ready if you don't already sort of have those things memorized. Next, you'll want kinetics equations. Ready for those? Don't think you're ready. Don't think you're ready. as Beyonce says. I don't think you're ready. Don't think you're ready. Some of the forces. Mass times acceleration. Some of the moments. Instagram alpha. If you don't have those memorized, I don't know what you're doing. Lastly, work and energy portion of the course, we did things like T1 plus V1 plus U1 to 2 equals T2 plus V2. All you really have to know for this work and energy is what each one of these variables represents and how to kind of work with it. T, this is your kinetic energy, and this is 1/2 m velocity at the center of gravity squared plus 1/2 mass moment of inertia about the center of gravity times the angular velocity squared. Your potential energy V could have combinations of both gravitational potential energy and the energy of a spring, usually written as mgh plus 1/2 kx squared, where x is the original minus final spring length. All right. Finally, your work term, which is the work of external forces, U1 to 2. This here is something like a combination of forces which act along the path. So here F dotted with dr, plus integral of the moments which act along the angular path d theta. More commonly, you sort of resolve these guys into components, but I'm going to leave that as a general equation for now. That's really all I think you are going to need for this test. Most of those things I would hope that you sort of have memorized at this point. We've done them enough on homeworks, you've seen them enough times through example problems and stuff in the class that hopefully those guys are burned in there like a brand onto your brain. Okay. All right. So what I want to do today, we'll go through 2 example problems, one for kinetics and one for work and energy. I'll pick off problems from the example problems that I posted online. So let's go ahead and do some of those. The practice problems that I posted online, I'll just kind of pull this up here, is this document here. All right, so a couple kinetics problems, 1 through 4 are kinetics problems, and then 5, 6, and 7 are work and energy problems. So maybe we do one of these, 1 through 4, and one of them from 5 through 7. I'll just say I think 1 is a little bit long. There's a lot going on with number 1. I wouldn't expect a problem of that sort of like length time-wise, because you have to propagate a lot of information between links, and I will say generally that problem's a little bit too long probably for a test. I think 2 is a good problem for a test. I think 3 is a good problem for a test. 4 is kind of a random one that I think is applicability to the real world, where you have kind of like a blade out incident in a turbine. So that one's kind of an anomaly also. I wouldn't expect something kind of that crazy on a test if I were you. I think 2 and 3 are good representations of kinetics for this portion of the class. So I'll take votes on whether maybe we do number 2 or number 3. So let's go to the chat and just vote what you think. All right. Pi equals E equals 3. Engineer's constant. Exactly. All right. So Mika wants 3. Other votes. 3, 3. Lots of 3s. So I guess we'll do number 2. Just kidding. I have 4 votes for number 3. The irony there is palpable. Nobody else really cares? All right, well, sorry, Caleb, you're outmatched. I know you're big and strong, but they overpowered you here. All right, so let's go through number 3 then. Number 3's got a lot to it. There's kinetics, there's kinematics, there's forces that you have to solve for. So I think this is a good problem to kind of work through anyways. All right. So I'll blow this up a little bit, give you a chance to get it down on your paper. if you haven't had a chance to look at it yet. And then I'll transfer the information over to my white pad and we'll work our way through it. Okay. So I'll get the information down here. Sorry if you were kind of copying. I'll keep the figure here. This is problem number 3. I'll get the figure up here. All right. So we've kind of got this rod that's connected to a pin at A, which A is sliding inside of a roller. All right. So we're told some information about the mass of the rod. So let's get that down here. The mass of the rod is 12 kilograms. And we're told that it is released from rest when theta is 0. All right, so if theta is 0, it means it's sort of in this horizontal kind of configuration. All right, we want to find what is the acceleration at point A, the angular velocity of this object, and the force exerted at A right after release. All right, sweet. This problem's got a little bit of everything, so I kind of like this problem. First things first, this pin at A, this guy is sliding within this slot. So if we have our traditional coordinate system, which is like the XY coordinate system, which I don't know why you'd pick anything else for this problem, we would notice that point A here is kind of constricted to this horizontal path, right? So if A is constricted to this horizontal path, then we have this kinematic relationship first off, which is note that the acceleration of A is restricted to only the I direction. So it's the magnitude of A solely in I hat. The new Apple product coming to a store near you. I hat. Okay. That was a good one. All right. I entertained myself. Let's do some kinetics. Now remember, when you're doing kinetics, you're going to want to do a free body diagram and a kinetic diagram. I know we're getting a little complicated now when we're talking about like kinetics and then work and energy. You have like a state 1 and a state 2. And then for our momentum that we've been talking about, you have like initial momentum, impulses, final momentum. So it's a little bit unknown maybe what you want to be doing in these types of problems. Here we have kind of a kinetics problem, so that's going to indicate to us that we want to do like a free body diagram and a kinetic diagram. So free body diagram. Well, we're told that it's released from rest in the horizontal position. So let's draw it. Oh God, let's draw this slender rod in the horizontal position. So here we are. Over here is this point A of interest, and also for these kinetic problems, the center of gravity is always a point of interest. All right, the forces that we have working on this guy, point A is like sliding in this slot, so this is kind of like a roller, and it's going to be free to move in the X direction, but restricted in the Y direction. So here we have a force that the slot exerts on this point A, so we have a force at A in the Y direction. We also have the weight of this object at the center of gravity. So here, this is the weight. And we're told that this thing has 12 kilograms, so we could convert that to weight using the gravitational constant. All right, next, kinetic diagram. For these kinetics problems, I advocate to always do your work at the center of gravity. So here's G, and I will draw my arbitrary kinetic components at point G. So here, this is the mass times the acceleration of the sky in the y direction at point G. And here, mass times the acceleration in the x direction at point G. Take it to the max. And I will draw a positive, arbitrarily positive, not IG omega, that's momentum, silly. IG alpha. Instagram alpha. I should make that my Instagram handle. Instagram alpha. Only you guys will get that. And we're not friends on Instagram, it's too bad. I have the best quarantine pictures, the best. So I've drawn it in this arbitrary positive configuration. It's pretty obvious to see that if we're going to examine this problem physically, when we drop that rod, it's going to kind of rotate in a clockwise fashion. So let's hope that the math tells us that the value of alpha, as we have drawn it, should pop out to be negative. But we'll assume that it's positive for now and roll with this and just cross our fingers about the math. Not cross our fingers. Come on. We know we're going to get it right. We don't need to cross anything. Except when you're doing cross products. We have information here, and we know that we need to do our analysis at the center of gravity, which is point G. So I have information about the acceleration at A, and I want to relate that to information at point G through kinematics. So we need kinematic relationship. To relate the acceleration at A to the acceleration at G. So I have some information about the acceleration at A, and I want to propagate that information to point G. So I'm going to do that with relative acceleration equations. So that general relationship is the acceleration at point G is the acceleration at point A plus alpha crossed position vector locating G from A plus omega cross position vector locating G from A. All right. Let's whittle this down. I know that the acceleration at A is contained only to the I hat direction. So here we have the acceleration at A only in I hat. All right, that come from the kind of constraints of the problem. Now I want to look at this back end term here, the omega cross R. If my bar is just being released from rest, it has not yet accumulated any velocity. It is about to have some velocity, but it does not yet have velocity. Okay, so in this particular snapshot in time, we have zero angular velocity in this case. This comes up a lot with these kinetic problems where it's like, you know, something is being held and then a pin breaks or a rope snaps or it's released from rest or so on and so forth. Like, you don't quite have velocity yet, but you're about to. All right, so that means that your acceleration component is non-zero, but your velocity component is zero. Maybe that'll come up on the test. Maybe. All right, so let's execute. Acceleration at G, given information about the acceleration at A. Here's the magnitude, the acceleration A at I hat. I don't know what it is. I'm looking to solve for that. Plus here the second term, which is alpha k hat, crossed with my position vector that locates G from A. Well, if I go back to my picture here, the position vector that locates G from A is here. Here's the position vector that locates G from A. Arja. That is just going to be half the length of the rod. So the rod is 0.6 meters, so half of that length is 0.3 meters. And it's just going to be 0.3 meters in I hat. All right. So working through this. This is the magnitude of the acceleration of A in I hat. Here plus K cross I, so positive J. So here we'll have a plus 0.3 alpha J hat. This is sort of an intermediate piece of information that I need to make my way through the problem. Let's call this equation number 1. All right. How are we doing on that? Hopefully we have enough kind of practice with kinematics that we're okay with that portion. All right, now I need my kinetics. Kinetics equations are like some of the forces is mass times acceleration, some of the moments is IG alpha. So let's go for that. Some of the forces x is MAX, specifically at point G. Okay, let's go to my figure. I don't have any forces in the x direction. So by sum of the forces x is 0. No crazy like a fox in this problem. Equals the mass of my rod I'm given. The acceleration at point G in the x direction. Okay, well, I saw that previously. Here's the acceleration of point G in the x direction. It is just the magnitude of the acceleration of A. So here, this is the magnitude of the acceleration of A. So 0 equals m times the acceleration of A. All right, well, that's pretty obvious. We can conclude here then that the magnitude of the acceleration of A is 0, or we can write straight away that the acceleration of A is 0. All right, that was something I was asked to solve for in this problem. So we're making our way. We're getting there. Moving on. Next kinetic equation. Sum of the forces in y is mass times acceleration y for point G. Up to my figure. I've got this reaction from the roller in the y direction. I've got the weight acting at the center of gravity. So here, this is the force at A in the y direction minus the weight of this object equal to the mass of this object times the acceleration of y at point G. Well, I have this kinematic relationship for that I saw previously. That's 0.3 alpha. All right, so we can put in some numbers here. We're told that this guy has a mass of 12 kilograms. So I can go ahead with that here. FAY minus 12 kilograms times 9.81 meters per second squared equals 12 kilograms times 0.3 alpha. Here I have two unknowns in one equation, so I just kind of whittle this down and kind of solve for one of the unknowns. So let's solve for FAY. And this here is going to be 3.6 alpha minus this weight contribution, which is 117.7 units on this newtons. Let's call this equation 2. So I haven't quite whittled this force in the y direction and this angular acceleration down yet, but I have one more equation, luckily. And my last equation is my last kinetics equation, which is the sum of the moments is IG alpha. Some of the moments here, again, I have to focus my analysis at point G. So the analysis at point G. The only force that will contribute to a moment at G is this force at A in the y direction, and that's located at half of the distance away from point G. So we recall that that's 0.3 meters. And when I kind of go by my right-hand rule, I'm going to see that the contribution of this moment is going to be negative. So here I have a negative FAY times 0.3 meters equal to IG. This is the mass moment of inertia of a slender member. So this will be 1/12 mass of the rod, 12 kilograms times the length of the rod, 0.6 meters squared, times my value of alpha. All right. I've got two unknowns here, but I can use equation 2 to plug in for FAY here. So I will do that. I will do that thing. And make that substitution. Negative FAY, which is 3.6 alpha minus 117.7 times my 0.3 meters equals all this mumbo jumbo in front of alpha. I got it here, I promise. It's 0.36. I guess I could have figured that out by canceling these two guys, but I'm old. Leave me alone. 0.36 times fish. Ah, boy. This gets me that the angular acceleration of this particular piece is, yay, negative 24.5 radians per second squared, or if you like in vector form, this alpha, negative 24.5 k hat rads per second squared. That's rad. Last thing that I need to do is I need to go back to equation number 2 and plug this value in so that I can solve for the force at A in the y direction. So back into equation 2 will get me that the force at A in the y direction is going to be 3.6 times alpha, which is negative 24.5, plus this contribution of the weight, so 117.7. This gets me that the force at A in the y direction after executing this, 28.8 newtons. Much better than old tons. All right. Questions on this guy. We got kinematics, we got kinetics, we got mass moment of inertia, angular acceleration, starting from rest, rawr, lots of stuff. Stuff. No questions. Everybody knows everything. Yes. All right, well, that was our kinetics problem. Let's do a work and energy problem. I would do any of the 3 work and energy problems. So here we've got this wheel on a hub rolling down a ramp. That's number 5. Weighs 32.2 pounds. Pretty suspicious. This one's a little bit more involved. Maybe this is a good one to do because it has a lot of stuff. We've got a rod and a disc rigidly attached, and we're asked about information for this system when the rod is kind of moved to the bottom of this configuration. All right, so that's kind of interesting. And then problem number 7, it's kind of your classic spring and rod sort of problem release from rest. Do we have votes? Votes in the chat. Anybody awake? Sorry, I guess I probably could have shown these. So here's problem number 5 with sort of like this wheel and hub rolling down a ramp. Here's 6 with sort of a rod attached to a disc rigidly, sort of hanging out above this datum, and then it rotates so that the rod's below it. And here's problem number 7. It's your classic spring and rod problem. Number 7 is a lot like number 3 from the homework, so let's not do number 7. I think number 6 is interesting just because there's a lot going on for number 6. Maybe we do number 6. Ooh, lots of 6s. Yeah, more 6s than 5s. Lucas got the mean face. Wow. Joe, giving him the business. Oh, wow, 2 mean faces. I'll pile on. Dang it, Lucas. Roar. Okay, well, there's the problem. I'll give you 30 seconds or so maybe to copy it. While I take out my aggression on Lucas here. Sorry, Lucas. Oy. All right. Let's get this guy out of here, and I'll get the information down. So here we have example problem number 6. All right, let's get the figure in here so we can figure out this problem. Information from the problem that is given to us. Let me get my problem up here. All right. The rod weighs 4 pounds. The disc weighs 12 pounds. We're told it starts from rest. And we're also told that there's a frictional moment that sort of slows this guy as it sort of moves from position 1 to position 2. And frictional moment at pin, which is, I'll label M, and it's 10 inch-pounds. All right, we want to find omega after 180 degrees of rotation. So that is when this rod is moved down to this bottom configuration here. So this here is kind of state number 2. So I'll fill in this guy. We want to know what's going on after that rod has kind of made its way to the bottom. So here with the rod in its upright orientation, this is state number 1. Down here, this will be state number 2. This is a work and energy problem because we're moving from one initial state that we know down to another state that we know. We're changing height. That's usually a good indication that this will be a work energy problem. All right. For work energy problems, usually we need to define a datum. So let's go ahead and define a datum here. I'll do it right at the pin at O. You could do it at location 1 or location 2. Your answer will be the same. The location of the datum is not really all that critical, but here I'm just going to set it at kind of at this pin at O. All right, let's make our way. So with conservation of energy, we know that we're going to use the conservation of energy equation, which is T1 plus V1 plus U1 to 2 is T2 plus V2. All right. Let's just whittle away at these constants, or these values. T1, this is my kinetic energy in state number 1, 0. It's because I'm told that it's starting from rest. I'm like nudging it out of this quasi-static sort of condition. So this is from rest. All right, always nice when we can write a 0 on the paper. Alex says, rest, baby! No rest for the wicked. The rolling stone gathers no moss. From rest. All right, V1. Here we could have contributions from springs or gravitational energy. We ain't got no springs. All right, all we got to worry about is gravity. Here this will be MGH1, and I could have gravitational potential energy both for the disk or for the rod. In this situation, the disk has a center of gravity that's sort of right here in the middle at point O, which lies right at the datum and doesn't go anywhere. So I don't really have to worry about gravitational potential energy of the disk. It's fixed, nothing really associated. All right. However, this rod is going to move from what is this upper configuration to the lower configuration. Its center of gravity here in state number 1 moves down to here in state number 2. All right, so I need to sort of accommodate for this change in the height of this rod. So I've defined my datum sort of at the middle here at point O. So my first height for this piece is going to be here. I'll call this H1. All right. So this will be the mass of the rod times the acceleration of gravity, which is just the weight of the rod. So here this is 4 pounds. Times this H1 value, and I'm going to work in feet. So here is 8 inches, which is the radius of this disc, which sort of tells me where the right edge of this bar is, and it's at a 30-degree angle. So we're going to have 8 inches times the sine of 30 degrees, but I'm going to convert into feet. So this will be 8 divided by 12 feet multiplied by the sine of 30 degrees. Put this all together and you'll have a potential energy. Why 2? Why did I write a 2? A potential energy in state number 1, which is 4 times 2/3 times sine 30, which is 4 times 1/3, or this is 1.33 foot-pounds. All right, continuing. My work term, U1 to 2. There aren't any external forces that are acting over distance in this problem. I will have some forces at the pin at the center there that are acting, but they're not traveling with either of the objects. All right, so those forces aren't doing any work. The only force that's doing work here is this frictional moment that's at the center that's resisting my motion. So I will have a term here that's something like the integral of the moment d theta, where that moment is the frictional moment that's provided. So my bounds on my integral here, since I'm rotating 180 degrees, 0 to pi, and the moment that's acting is 10 inch-pounds, and it's opposing the direction of motion. So if I think about my wheel sort of turning this way, the friction is going to oppose that motion. So I have to provide a negative sign here. So this is 10 inch-pounds given in the problem, and I'm going to divide by 12 so that I can get to feet. If I do this, I'll find that U1 to 2 is equal in magnitude here to negative 2.62 foot-pounds. How are we doing? That always seems to be the problem. The work term just always seems to be the issue. All right? We all got issues. This U1 to 2 seems to be an issue. All right, so T1, V1, U1 to 2. Now let's continue. I'll look at T2 last because it's the most complicated. So let's do V2, which will be mgh2, where h2 here is the distance that this bar is below the datum. So here's h2. And since it's below the datum, I'll need a negative sign. So here, this is the mass times the gravity of the rod, which is together 4 pounds, multiplied by the height that this is below. So here again, we have a negative sign, 8 on 12 times the sine 30 degrees, much like we had for the gravitational potential energy in situation number 1. So do the hokey pokey, turn myself around, negative 1.33 foot-pounds is what it's all about. Do the hokey pokey. Lastly, the hardest part about this problem, which is the kinetic energy of this entire system in state number 2. So let's talk about it. It's going to be a combination of the potential energy from the rod and the potential energy from the disk. So let's look at each one of those 2 possible contributions. We know the general equation is something like 1/2 mass of the object, velocity at the center of the object squared, plus 1/2 ig omega squared. And let's look at the disk. We'll add to that the kinetic energy from the rod, 1/2 mass of the rod, velocity at the center of gravity rod squared, plus 1/2 mass moment of inertia of the rod times the angular velocity of the rod squared. All right. All in kind of condition 2 or state 2. We can simplify a little bit. This disk, it's fixed to that pin at O. It ain't moving. All right, it's fixed. So there's no velocity at the center of gravity for my disk. That thing doesn't move linearly in any way. It's only rotating, right? Next, all these other components I will have. All right, so angular acceleration of the disk, yup. Angular acceleration of the rod, yup. And the linear velocity at the center of gravity of the rod, yup. All right, so we got to worry about all these things. To proceed with the problem, I'm going to need some kinematic relationships. All right, so need kinematics. And that is, I need to relate the velocity at the center of gravity of the rod to the angular velocity of the piece. Well, I can do that by understanding that this rod, the center of gravity, is going to have like fixed axis rotation about the center of this thing, about point O. I kind of go up to this figure. Here's the center of gravity of the rod. and it's got fixed axis rotation about 0.0. So it's going to kind of have, you know, this circular path generally about 0.0. All right, so it's got fixed axis rotation about 0.0, and the radius or the arm length between O and the center of gravity is this h1 value. Okay, so we can say then that the velocity of the center of gravity is going to be the angular velocity of the piece multiplied by h1. So this is angular velocity of the piece times 8 on 12 times the sine of 30. So we'll have here that the velocity at the center of gravity is related to the angular velocity generally of the piece, which will be 1/3 omega. How are we doing on that? Okay on that? Got to know those kinematics. I'm going to make that substitution. This is, I'll be specific, the velocity at the center of gravity of the rod. Right. So I'm going to make this substitution here. Right. So I'm ready for T2. This term first. 1/2 mass moment of inertia of a disk is 1/2 mr squared. So this is 1/2 mass of the disk is 12 pounds divided by 32.2 feet per second squared. I need mass multiplied by the radius of the disk, which is 8 inches divided by 12 to get into feet squared. That is my mass moment of inertia of the disk. Let's be clear here. All right. All this multiplied by the angular velocity of the piece squared. Next term I'm going to concern myself with is this term here, which is the kinetic energy associated with linear motion of the center of gravity of the rod. So here this will be plus this second term, which is 1/2 mass of the rod, it's 4 pounds by 32.2, multiplied by the velocity at the center of gravity of the rod. I'm again going to make this substitution here, which is 1/3 omega. Squared. All right. So this kind of here is this second term here. All right. Lastly, I'll add to this final kinetic energy associated with angular motion of the rod. Some of you might be thinking, does the rod have angular motion? Yes, all points on the rigid bodies, as they're rigidly attached, have the same angular velocity, which is omega. So yes, the rod has angular velocity. 1/2 mass of the rod, pounds, 32.2, multiplied by the, sorry, I need to go back here. The mass moment of inertia of a rod is 1/12, forgot the 1/12. Mass of the rod, 4 pounds, divided by 32.2, times the length of the rod squared. Okay, well that is a little bit complicated. We need the length of the rod squared here to fill out our mass moment of inertia. All right, so we need this length here. Well, that length is going to be 2 times this length. And that 1/2 L is just 8 times the cosine of 30, right? So here, the total length of the rod is going to be 16 inches on 12 to get me in feet, multiplied by the cosine, 30 degrees. This is the length of the rod, all squared, multiplied by, can't forget your angular velocity of the rod, squared. Everyone all right with that? Okay. Let's look at what each one of these contributions would be. I think it's just kind of an interesting exercise. So let's kind of look at the 3 terms here and what their relative contributions are to the total kinetic energy in state number 2. So here we'll have this first term is something, oh wow, that's a red line. So this first term here, I gotta get this up. Oh, I didn't even punch it in. I need my calculator. Where's my calculator? First term here, 0.0414 omega squared. The second term here, you can do for yourself. Is plus 0.0069 omega squared. The third term will match 0.0069 omega squared. There are reasons why that is, but I don't care to go into those quite yet. So what do we see here? Well, remember that this term here was from angular motion of the disk. This is the contribution from linear motion of rod. And this is the contribution from angular motion of the rod. So their relative, the disk is dominating the kinetic energy term. All right, it's almost 10 times as much as the other two terms. So it's really the sort of angular energy of this disk that's dominating, and that's mostly because the disk weighs a lot more than the rod, right? So after adding all these together, you'll end up with a T2 of 0.55. Sorry, I missed a zero. 0.0552 omega squared. All right. So we got all our terms now to fill out our conservation of energy equation. We've got T2 here. We've got V2. We've got U1 to 2. We've got V1. And we've got T1. We got it all, baby. More than just good looks. We got everything. Got a personality too. Dang it. So, ready. T1. 0. Bam. Plus gravitational potential energy. State number 1. 1.33. Bam. Plus the work, which is opposing motion because we have friction. Need that negative sign. It's going to be 2.62 equal to T2, which is 0.0552 omega squared. It contains our omega variable that we're looking for, plus my potential energy at state number 2, which we found to be negative 1.33. The units on this equation here, foot-pounds. After the dust clears and we solve for omega, we have omega is going to be 0.85 radians per second. So it's moving pretty slowly when it gets to the bottom. And there's a pretty big frictional term here that's slowing everything down. All right, so we almost have so much friction in this bearing, or whatever you want to call it, that it's almost not getting to the bottom, right? It's a very slow angular velocity because there's so much friction in that particular bearing. All right, questions? If not, study up, work hard, do the things, come early tomorrow, have all your stuff prepared, be ready to dominate, crush grapes, all the things. Thanks for coming today.